Welcome to Holyfield Physics TV, and today we're going to look at Hubble's law, and this is part of the A2 cosmology unit. First thing we need to look at is emission spectra. As you all know, atoms have discrete energy levels that their electrons can be at. We can excite the electrons to higher energy states. Once we've done this, the electrons can fall back down again, and when they do, they'll emit specific photons. Now each photon has an energy that's given by the famous equation E equals hf. Photon energy equals Planck's constant times the frequency. So if we look at an individual atom with a whole bunch of different energy levels, we'll get a big energy change, E4 down to E0, gives us a high frequency, short wavelength blue photon. Energy change from E3 down to E0, not so large, and therefore we have a longer wavelength photon. E2 down to E0, again, that's smaller still. Still get a photon, but this time it's even longer wavelength. And then finally we get E1 down to E0, longest wavelength of all, and it's at the red end of the spectrum. These four energy levels give rise to specific colours, specific spectral lines, or characteristic emission spectra for this atom. And the emission spectra behaves very much like a fingerprint. If we see this spectrum, we know which element we have. Things are a little bit different with the light coming from a star though. Let's look at our sun. Here's the stellar radiation reaching us. And because the star is so dense, there are an awful lot more, pretty much an infinite number, of energy levels the electrons can have. And so we get a continuous spectrum. Just like using a prism, seeing the nice, pretty rainbow pattern on the wall. The atmosphere of the star, though, is less dense. And so there are less energy levels available for the electrons. So atoms in the outer atmosphere will absorb photons coming from inside the star, re-radiate them, but in lots of different directions. And the effect of this is that less of those photons reach us here on Earth. And so we get a dark line in the continuous spectrum. Here's a typical stellar absorption spectrum. And beneath it, we've got the emission spectra for a number of different elements. Now, as you can see, the emission spectra match up precisely with the absorption spectrum. The conclusion we can draw from this is that the atmosphere of the star, in this case, must contain helium and must contain carbon. Hubble used this idea of absorption spectra when he was looking at distant galaxies. And what he found was that the dark lines in the spectra had been shifted when he compared them to the emission spectra of elements here on Earth. And each of the lines had been shifted by the same percentage amount. In this case, we'll call it delta lambda. And what he realised pretty quickly was that this was due to the Doppler effect. And that's the effect of a moving source moving away from us, light or sound, having its wavelength stretched. If it's moving towards us, the wavelength is going to be compressed. And the equation that we have for the Doppler effect is V over c, the velocity over the speed of light, equals the change in wavelength divided by the original wavelength. And if we rearrange that, we get the recessional velocity of the galaxy equal to delta lambda over lambda times the speed of light c. What he did next, however, was the really important thing for us. And he plotted redshift against the distance. Now, distance, because we're talking about galaxies, measured in megaparsecs, millions of parsecs. The redshift relates directly to the recessional velocity. So this is what he plotted. And his results absolutely astounded him. He got a perfect straight line. Gradient of that line, recessional velocity against distance, is what we now call Hubble's constant, H0. And it has some funny units. Kilometers per second per megaparsec. And Hubble's law, recessional velocity v equals Hubble's constant times the distance. Now you'll have to change those usual units for Hubble's constant, kilometers per second per megaparsec, into SI units, the units per second. So here's how we do it. First thing we'll do is change the kilometers per second into meters per second. So we have 72,000 meters per second per megaparsec. Next thing is to change per megaparsecs into per meters. So 1 parsec is 3.1 times 10 to the 16 meters, megaparsec 3.1 times 10 to the 22 meters. So we'll divide by this figure. And we end up with a very small number indeed, 2.3 times 10 to the minus 18 per seconds. This is the Hubble constant in SI units. What should we do with this data? Well, let's look at two different galaxies. One's twice as far away as the other. From Hubble's law, we know that one that's twice as far away has twice the recessional velocity, indicated by the arrows there. And what we're going to do is wind time backwards. Let's go back 1 billion years. As you can see, both galaxies will be closer to Earth. The further galaxy still moving away from Earth faster, still twice as fast. But let's wind it back some more. And they're both getting closer and closer. Now what you can imagine is if we keep winding time back in this way, both of those galaxies and the Earth will be in the same place. It goes a lot further than this though, because it's every galaxy. And so this time, when the whole of the universe, every single galaxy, everything that's out there, was in one place, is the moment of creation. And that's the time that we call the Big Bang. If we take the reciprocal of Hubble's constant, that gives us the time since the universe was all in one place. In other words, it gives us the age of the universe. And if we work this out, we take our per second value for the Hubble constant and take the reciprocal. The figure comes out to be 13.7 billion years. That's the time when all of the universe, every single thing in it, was in the same place at the same time. In other words, it was the start of our universe. Thanks very much for watching and listening. I'm Richard Gould. This has been Holyfield Physics TV. Work hard, do well in your exams.